Good evening. Welcome all to this evening's webinar on methods, optimising outcomes and exploring relations. My name is Brian Lann and I'm your host for the webinar this evening. You're hearing from two expert presenters. Stephen Crouch is at Frankston High School. You can see on his bio there that he's presently teaching years 11 and 12 after considerable study in mathematics, physics and astrophysics. He teaches methods and specialist, and also, of course, an expert on the use of TI-nspire. Ray Rosen from RMIT University, also an expert on TI-nspire, and developed some fantastic files, and I do know that some of the material that Ray will be sharing with us this evening, I was lucky enough to see firsthand at a session of his that I attended last year. Some very clever ideas. And in addition to all the mathematics, he's also not a bad table tennis player. You there, gentlemen?
Yes, we're here. Okay, so you can see my desktop at the moment. My name's Raymond Rosen, and what we're going to do tonight is look at some optimisation, or what are commonly called maxima and minima problems. We're going to look at these in a number of ways through the traditional calculus method, as well as sort of like a graphical approach where we can also use the data capture facility, which will be a new one to some people. So I've got a lot of worked examples I want to work through here. Most of them are all very much the same sort of approach. So I'll work through a simple one, and then we'll talk about the ladder one and some of the other problems that we've got mentioned. So the first problem I want to work through tonight here is if we've got an isosceles triangle with one vertex at the origin and two on the curve y equals 9 minus x squared, one side of the triangle's got to be parallel to the x-axis. What we want to do is we want to find the maximum or the largest possible area of that triangle. So we'll work through this problem. So I've already plotted the graph of 9 minus x squared to save a minute or two. But what we want to do now is we want to do this sort of graphically and show what's going to happen when we do it algebraically and with calculus as well. So a number of things that we want to do here. First of all, I want to put a point anywhere on that parabola, 9 minus x squared. So we'll use the geometry and the point on tool. So geometry points, point on. So I'll stick a point anywhere on that parabola. I'll stick that and press enter. That'll anchor it. Notice in the corner the icon is still there, so when we press the escape key, that will then disappear. Now the coordinates of that point are displayed. Perhaps I should have had another point there for the origin, which we'll put in as well. So we'll put the origin in here as well, which is the origin. Again, anchor that one in. Coordinates of that one are not shown, so we'll use the control menu as a feature we'll be using often here to stick that coordinates of that point. Now the other point is got to be the reflection in the y-axis. It's got to be the point so that that line there is parallel to the x-axis. So we can generate that point by going menu, geometry now, and here we're looking at our construction. No, we're going to look at a transformation, aren't we? We're going to look at a transformation, which is the reflection, and you can see the little picture there in the red and the blue, reflection of that point. So if I click on that point, and now click on the y-axis, I've got that point being reflected in the y-axis there. Okay, so now I can join up my 3 points, the origin and those 2 points, with a triangle. So menu, geometry, and what do we want now? We want some shapes. A triangle. So I'll click on the first point, the second point, the third point, and then I'll also click on the last point again just to be on the safe side. Sometimes you might have to use the polygon tool rather than the triangle tool for a square or something like that. Okay, so press escape again to get rid of that. Alright, now it looks very nice, that triangle. As we can see, we can move this point and the area and the triangle will change. What I think is nice if we use the colour feature here, so we'll choose the colour feature to colour the triangle and also fill it in. So control menu is one that's used often to get the properties, and then the fill colour. So now I've got that triangle filled in as a triangle shaded nice and pink. Alright, now the x value here is the one which we're going to be moving along. So we're moving this point here. We can't move that point. So what I want to do is I want to give this point a value. So I'll click on this point, and again, using a control menu, this time I'll go store. So we'll give that x value a value. I'll call it, say, xc for x coordinate, because I don't like using x's because that gets a bit confusing. So that is the value linked to xc. Now we want to measure the area of this triangle as well. So once again, we'll use the geometry tools here. Which one are we going to use this time? Measurement and area. So geometry, measurement, area. And if we just click on that triangle and press the enter, we see that the area of the triangle is displayed. Again, pressing escape so we don't want to measure anything else. So we'll move this one just out of the way a little bit. Now also these coordinates are 2 decimal places. Again, using control menu, I can change the attributes of those to make it a little bit more decimal places. Probably 4's enough. And again, on this one, I'll change the attributes of this one by pressing the green arrow on the side here. There are plenty of decimal places there. Oh, that didn't work. Anyway. Alright, so now again, we also want to store this one and give this one a value. So we'll do the same thing that we did before. So store this one to a variable. So I'll call this one area of this triangle. And press enter. And just move it away. Alright, so we can see now that when I move this triangle, when I move the point, the area of the triangle is changing and the point is changing as well. So what we're going to do now is we're going to capture all those values into a spreadsheet. Alright, so let's open up a data and statistics page here. Okay, now the values up the top here, the names of the cells are not the formulas, and we can't use the values xc and the area of the triangle for the values that we used. So we have to call them something else here. So I'll call this one, say, x value, not the xc, and in column B, I'll just simply call that area. Okay, now the second, that's the name of the cell in the top one there. And these ones here are where we put in some formulas. So with my cursor in this cell here, notice also the menu is now context sensitive for the spreadsheet. So when I press the menu here, we get a different set of menus. So the menu here that I want is data. And what I want to do is I want to do a data capture. I can either do data capture automatic or I can do a data capture manual. Manual means basically one at a time. So we really want data capture automatic here. Notice down the bottom we've got x value equals capture var. Now if I couldn't remember the name of my variable, and sometimes you have variable names and spell them incorrectly, it's best just to get your variables from the var button. So when I press the var button, what I've got here is I want to get the xc value. So notice it's got a little quote in it in front of it. I think that's just referring to that it's not column xc or something like that. So pressing enter now, notice I've got one value in there. That value 2.061, if we look back at my diagram, happens to be the x value that I've got. So this data capture is a very nice little feature that we're going to be using. The same thing in this cell here. Let's repeat that again and go menu, data, data capture, option number 2, again automatic. The variable that I want to capture this time is the area of the triangle. So once again we'll press our var key and we'll choose area of triangle. That'll paste that in and press enter. Alright, now this has only got one value in it, but when I come back now and I move my value of this point, which I can move this very, very slowly backwards and forwards, and when I now go to my spreadsheet, all the values are now captured. So we've got like 300, oh I don't know how many values, but at least 170 or so values plotted there in that value. So what we're going to do now is actually plot those values on a graphs page. Okay, so we're going to plot these. When I plot these, I'm not plotting a function here. What I'm plotting is actually a, what am I doing? I'm plotting a scatter plot. So graph entry edit, option number 6, I'm plotting the scatter plot. So the X value here, now again, once in case you couldn't remember what it was called, it's best to press the var command, and we only get 2 options here because these are list variables and they're the only ones that we can actually do a plot of. So it's the X value for the X, move the cursor down to the Y, you have to plot 2 things here, and this time I'm also plotting the area. So when I press enter now, we will see a value. Now obviously the window function here is not the best, so we're going to have to change the window settings for these variables. So menu, Windows settings, the value of X was between 0 and 3, so we'll have say -1. I like to see a little bit more on the screen, so I'll go 4, 1, tabbing to the next screen. For the Y value, we'll say -2. But the area was sort of around about 10s and 12s and things like that, so I'll go up to 15. And in my Y scales, because I don't like seeing lots and lots of little dashes on the side of the screen, I'll press 3. So there we see the X, or the graph, of all those points in this thing that we've plotted here. So if we move back into here and actually move this even so we get a 0 area, we get a 0 area, we don't really know where. What we're trying to do here is we're trying to find the biggest area. So again, I'll just try to get that one with some more decimal places so that we can actually see the values. All right, so now we've got a nicer little graph here. So we want to find the maximum value of that. So having the list list values here, what I can actually type in here, I can actually type in max. Max is a nice reserved word which will find the maximum value in that list of numbers. So if I type max of area and return, that will tell me that maximum area was 10.933923. Doesn't give me the X value for which the maximum area occurs. So let's try to set this thing up with the formula as well to find out what's going on. So what is the area of this triangle? The area of a triangle is a half base times height. I've actually got 2 of them, so it's just a half of the X value times the Y value. So let's try to find a function which will then give me the same as the data plot of those points. So what I want to do here is define another function. I've already used the function f1 for the graph, so I'll use the function f2 now. And this function is the function that I want to maximize or minimize. So this function is really just x times the function f1 of x. Okay, so that's done that. Now, we know from calculus, well, the nice thing about this thing is that even if you don't know calculus here, you can still get the maximum value from the plotting that we've done before and the value for the maximum area. So it's a good idea also to link the calculus. So this one is a fairly simple one to do. So we want to differentiate that. We haven't even seen what the function f2 is, but we can see it. So let's see the function f2, whatever it is, f2 of x. There it is. Notice the calculator turns it around with a minus because f1 was at 9 minus x squared. So now we want to differentiate that function. Now there are lots of ways of performing the differentiation. We can get it from the calculus menu, we can get it from that template there next to the book. And let's move across to get the template for d by dx. Move your cursor into the bit here. And once again, if I don't want to get f2 and I couldn't remember what it was, I can always get it from the variables command as well. Okay, so that's the derivative. Now to find the value of x for which it's a maximum, what we have to do is we have to set this derivative equal to 0. So menu, algebra, and solve. I want to solve where that derivative, I don't even have to copy the actual equation in, I can just copy the derivative equal to 0, comma x, and solve that for x. Now, we should have realized that x was only a positive number, so I should have actually said, okay, x is greater than 0. And then that way we won't get the negative solution. So having found the value of x, which is root 3, which is the exact value, which is 1.732, we'll get an approximate for that value by pressing Control Enter. And now the maximum value is in fact the value of that function evaluated when x is equal to root 3. So I'll use the Control equals button to use this pipe symbol or the given symbol, given that x is equal to root 3. And that'll give me the exact area of this triangle for which it's a maximum. Again, Control Enter, 10.39, which happens to correspond to the value here. Now we'll see that when we plot this function here, that was the scatter plot of the points, but basically what I can also do here is to graph the actual function as well. So the function that we want to graph here is f2. And notice that f2 is a perfect fit for the data plot of all those points. So again, a nice little relation. I shouldn't have had that one in blue. Let's have that one in, say, a different colour so we can see them.
I really like the multiple representations there, Ray.
Yeah, that's what I'm
really
trying to get at, because you can do it.
Yeah.
And also, while we've got that function here, we might as well try to analyse the graph and find the maximum value on that graph as well. And there it is, 1.73, 10.4. Once again, we can increase the number of decimal places to those. 1.73 we realise as the exact value of root 3. And we'll just say colour that point a different colour as well, so we know that that is the maximum value. So you can try to get that that point. We'll try to 10.3, but we're not going to sort of get there. But this, I think, shows, as Brian was just saying, by moving this, you get the maximum area. Now, you can always do this again. If you want to get rid of these values, you can just do, again, a control menu and clear the data. So if I clear the data, that will then get rid of it all, and then if we go back to the graph, we might not see anything on the graph because I've cleared it again. We only see the 1 point. All right, so that method of actually finding the maximum and the minimum of a function or an application question is basically exactly the same, which I've got now a number of problems installed here. So I'll show you now a couple more problems that I've actually solved. And all of these are basically the same sort of procedure, maybe a little bit more complicated, but basically the same ideas that we've seen in that area of the triangle inscribed in that parabola. So if we think of some other questions here, find if we've got a circle of radius r and we want to inscribe a rectangle in it, and then we want to find the ratio of the largest rectangle to that of the circle. So the first time we actually work through this, we'll actually work through it. I've completed all these, and all these files will be available. There's lots of problems here. You could distribute these files, not finished, and get the students to do the data capture for that stage, and then they can see the graph and store it themselves. So what I've got here is a circle of radius 1, and again, I've licked a point on this circle, and by moving this point around, we can see that the area of the rectangle is going to change. So the same thing as what we did in the last one. We do the data capture of the x value and the area, and then we do a plot of the scatter plot of the points. Now, the area of the circle this time is 4 times x. So the area of the circle is x squared plus y squared equals 1. So the area of that circle is pi r squared, which is 1. This is the circle of radius 1. The area of the rectangle is 4x times y. So y is root 1 minus x squared. So that function, again, lies on those scatter plot points that we've done. Now, it's an interesting calculus problem if you want to try this one by having 4x root 1 minus x squared. That would require a product rule and a chain rule to differentiate it. To solve it when you put that equal to 0, it's nicer to have a common denominator to solve and find the value of x, which is root 2 on 2, and then working that out. Now, the nice thing is that when we work out the area of the rectangle to the circle, which was pi r squared, we get the value of 2 on pi. And this value is in fact independent of the radius. We could do the whole thing again with another circle, x squared plus y squared equals r squared, where r being any value, and inscribe a rectangle in there, get the value for the rectangle area and put it equal to 0, solve for x, and once again the ratio of the largest rectangle to that of the circle is 2 on pi, independent of the radius r. Alright, so there's some sort of nice, neat max-min problems. And also if we wanted to do it for an ellipse, the same sort of thing happens. You have to know the formula for an ellipse. The formula for the area of the ellipse is pi AB. So it's pi, the a squared is 81, the b squared is 25. So if we do the same thing for this question, as I said, I've already completed these, do the data capture, work it out, work out the area of the rectangle, and do the same thing. We'll actually get the points. The pink points are the scatter plot, and the blue curve is the curve that we're maximizing or minimizing. So once again, the same thing happens. We get the ratio of the area largest rectangle to that of the area of the ellipse, being pi AB, as 2 on pi. And if you want to generalize these examples, you can by working it out for x squared over a squared plus y squared over b squared equals 1. We can then solve that equation for y, and again work out the area to find the function f of x, because I'm not going to plot this one, because we can't plot it with a's and b's. And again, follow through all the working there, differentiate it, set it equal to 0. We get multiple solutions because the calculator is not really sure if it's a is x is positive, a is positive. So if we add in the constraints that a is positive and b is positive, we get the one solution for x. And again, we'll come up with the same answer with the ratio of the largest rectangle to that of the ellipse is again 2 on pi. All right, I'll just show you one or two more, which is very similar to the one we did. Before we did the triangle inscribed in the parabola 9 minus x squared. Well, this time we want to inscribe a rectangle in the parabola 9 minus x squared. And once again, we'll try to find the ratio of the largest area to that of the area bounded by the curve. So again, this one is completed. And when we work this one out, we do the same sort of thing. We can move the points along, and if we work this one out, we actually get the data capture. We get some points, 1.732, it looks like root 3 again. And the ratio of the largest area of the rectangle to that of the area bounded by the original curve is root 3 on 3. Now, the first time I worked through this, I'm thinking, well, we got 9 minus x squared, so it's no surprise that we're getting root 3. So the area bounded by the curve minus 3 to 3 of f1 is 36. So I'm thinking, yeah, this has all got to do with 3's. But again, there's some general results here. It doesn't matter if you have any parabola here, a squared minus x squared. The rectangle's dimensions are 2x times y, where y is f of x. Where a is any number here, if you differentiate that and set it equal to 0, solve for values of x, then once again, the ratio of the largest rectangle to that of the area bounded by that curve is still root 3 on 3, independent of values of a. So this is a nice little approach to doing some of these questions. Now, before we just quickly move on to the ladder problem, there's lots of problems I've got here. Notice that when we press Control up arrow, we can see like the sort of PowerPoint slides here. Another max-min problem that I thought of that when we did this is to look at this problem here. Find the point on the curve that is closest to the origin and find this closest or minimum distance. So again, set it up the same way. I've got the curve 9 minus x squared. The distance on the x-axis is 3. The distance on the y-axis here is 9. Is there a point which is closer than 3? Obviously, if I move up to here, the distance is 9. Again, this is just worked out exactly the same as what we did for the triangle, but rather than using the area tool this time, I've used the length tool to find the length of the line segment from the origin to that point P. If we look here, there is a point somewhere here which is smaller than 3. So I want to find this closest distance here. And once again, we're using the data capture method. plotting the points from the scatter plot and working out the minimum distance. So there's some nice sort of, again, the formula for the closest distance. The distance is x squared plus y squared, where y is f1 squared. So that gives me the scatter plot and the function, which again, the scatter plot points lie on the curve. So there's lots of nice little problems we can try here. We can try some generalizations of all those sort of problems, closest distance to points on curves, inserting in rectangles inside other types of curves. You can even put it inside trig graphs, cos graphs, or we could actually even put it inside e to the minus x squared graphs and do the same sort of thing. So all these files are very, very nice. One problem that I think we said we were going to look at here is the ladder problem. So let's just look at the ladder problem here again, which is a maximizer and minimizing problem. So if we've got two corridors, one of width 2 meters and one of width 3 meters, meeting to form a right-angled corner, we want to find the length of the longest ladder that can be carried around the corner. Now this one requires a bit of thought and investigation because it's actually a minimum problem, not a maximum problem, because the longest ladder is actually the shortest ladder that will touch the edges and the corner. So what we've got here is a nice little diagram, and again we've got two values. We've got a value x here, which is the corner distance, 2.45, and the longest ladder distance here, which is the length of the ladder, which is 7.063 in this case. So once again, this has been set up, and once we move this point, again we get some varying different values, and once again we can then plot as a scatter plot the value of x against the value of that length of the ladder. Again, all of these have been done in a data capture, and again, now this is the equation here to verify that this point here, 2.61, is the x value, and 7.023 is the longest ladder which touches the 2 points and the corner. The function here is a little bit trickier to calculate. It actually, I've got a little one here, which is a generalization of this problem here. So if we do a generalization of that problem from the beginning, if we think what's happening here, the ladder has got two lengths. It's got the length of the first bit and the length of the second bit, AC plus CB. If we generalize the corner lengths to, say, A and B, then by Pythagoras it was x squared plus b squared and y squared plus a squared. Now, a bit of thinking here will show you that the y value by similar triangles, a over y is equal to x over b, in which case we can substitute y is equal to a times b over x into there. So what we're doing is a typical here max-min type problem. The strategies involved for solving a max-min type problem are to sort of draw a diagram, allot any pronumerals that we think we're going to need, have a function which is going to be maximized or minimized, which is often in terms of two variables, eliminate one of the variables from some constraint, which may be geometric, get the function to be maximized or minimized now in terms of only one variable, simplify that function, and then differentiate that function and set it equal to 0. And that applies for both a maximum or a minimum function. Solve the equations, and often we have to be very, very concerned about the domains of these questions, because sometimes when we're looking at max-min problems, the maximum or the minimum may occur at the end point of the function. So differentiating this function, the algebra in this one can get extremely messy, especially for the general case, and then substituting that value back in. So this is why I think the CAS is very nice for this one. To find the function L, substitute the value for L for Y in terms of A and B. Notice we need the dot in there. And again, the calculator will simplify that expression for us. Differentiate that function, form a common denominator, set it equal to 0, and then substitute that value back in. So this will give me a general formula for the longest length of the ladder as a general case as a to the 2/3 plus b to the 2/3 all to the 3 on 2. There is actually another way of doing this problem from trigonometry, and that's by using the angle approach. So I think I'm actually going a little bit over time here, So let me just show you the other method of using this one. Rather than having a variable x and y, to have an angle here, theta. And I've got that in degrees. And a similar sort
just
of
on that diagram, Ray, it looks very impressive. We've got a question there. How did you draw the diagram?
Okay, well this is one I actually didn't draw. You can thank Peter Fox for this diagram. He actually drew this diagram. But I imagine it's just nice little straight lines and curves and points here, and then you're just measuring that distance between those 2 points, and again just finding the angle between these, the angle. There's an angle tool for measurement, just like there was the angle tool for finding the lengths and areas and things as well. So they're all available.
Because we are on a geometry page here, not a function page.
Yeah. So once again, we use the data capture and then try to plot the points. So this one is done in 2 ways. This latter problem can be done in 2 methods. One using the algebraic approach, and the other one by using the trigonometric approach. And this time I've actually solved it in degrees. You'll notice that it's in degrees. And when we differentiate sine and cos in degrees, you know you come up with this pi and 180 floating around out the top. So I've defined this function to be in degrees, and then I solved it, and I've got the value of x. This is for the particular case when the a's and b's were 3 and 2. But we've also got the general solution here, the general solution with a's and b's. You can actually solve these equations. I'll leave it to you, so I think we're running out of time here. But in the calculator, if we just define L of theta to be A over sine theta, B over cos theta, differentiate that, set that equal to 0, the calculator won't actually solve that equation because it's got A's and B's and thetas involved. But if we substitute the value of theta in, once again we come up with the same solution, or the same value, A to the 2/3 plus B to the 2/3 all to the 3 on 2. So I think I've sort of gone a bit over time. I think I'll hand it back to Stephen now to finish off with some paper folding. But hopefully there's lots of ideas here for lots and lots of different max-min type problems. There's lots of worked examples here. And we perhaps even could do this with a SAC. You know, we could have these max-min problems, a specific case, and then go to a general case of lots of other different types of max-min type problems and optimization problems. All right, so I think it's over to you, Stephen. Hopefully you've got enough time.
I'll send it over to Stephen. I'm just answering a couple of the questions that we've had there. Yeah. Ray, a lot of interest there, and for a lot of people, they hadn't seen the data capture before.
Yeah.
So that's a really good learning point there, and I know Stephen's going to show a little bit more of that too. So that's a great one to get. Someone also asked, how do we just generally draw the ellipse? So this is the tool here. What I've done here is just on a page. If I've got a graph page, then in the menu, when it's graph entry edit, well, we've been able to, for quite a while now, to be able to graph a relation, but these equation templates are handy. And the one down here, ellipse or hyperbola. So it just gives you that standard centre form, and the same sort of thing for the hyperbola. Put in the values to adjust. So I thought I'd just share that one.
Yep, that's how I did the ellipse on one of them. But then we also do the general cases, which I think is good, because students, you know, especially in sort of SAC applications, you do 1 or 2 worked examples, and they have to try to get the general situation to actually solve.
Yes. Yeah, and if we look at the sorts of exam questions that are being given, students are generally led into this. So they'll get get a specific case and then followed by general case. Stephen, are you right to share your screen and share with us what exercises you have for us?
Yes, sure
Paper
thing.
folding.
Thanks, Brian, and thanks, Raymond, as well, for your brilliant interactivities there and giving us all some ideas on how to use calculus properly. So what I'm doing with everyone today is another triangle activity, but not with a graph, but rather with some paper. And we can have Peter Fox again to thank for this one here. He's gone through and drawn the interactivity for us as well, just like Ray with the with the ladder problem. So let's make a move on it, shall we? So what we've actually got here is basically a piece of paper in landscape mode, an A4 piece of paper that is. And what we're doing is taking the top left corner of that and folding it down in such a way that that top left corner ends up on the base of the paper. And what you end up getting is a paper that looks like this. And what our job is to do is to try and maximize the area of that gray triangle that's sitting right there. So we'll go through the maths of it. We'll go through a couple of diagrams. We'll go through the function. We'll do a bit of data capture as well, just to repeat what Ray was doing before. And then we'll end up with a general idea of how to maximize the area of that. So let's make what we can do before even starting is actually see this in an interactive form. So what we've got is a point P over here, and that point P represents the height of the triangle that we have. So if you can just imagine this big rectangle there to be representing the A4 piece of paper, and the point P is the point along the left-hand side at which the fold in the paper ends. What we end up having is basically a triangle generated from the remaining side of the slide, as well as the height here of the triangle and the base as well. So as you can see, as you change the value, change the location of P, you end up with many different triangles. And our job is to try and get the maximum possible area of that triangle there. So we can just have a look at that number of there called area. And as we move the point P, you can see it starts at 0 when the fold is fully completed. And then as we start changing the value of the fold, you can see the area increasing up to about 42.4 or so, and then it slowly starts coming down again. So we have a general idea of what the maximum area is, as well as the height at which this area occurs. So what we're going to do to set up the mathematics behind this is use a diagram like this. So an A4 piece of paper is basically 30 centimeters in length and 21 centimeters in width. What we're going to do is set up x to be the variable representing the height of our required triangle, because this is our focus triangle there. We have the base of the triangle that also depends on x, and we also have the hypotenuse of this triangle. What we need to really get an idea of is a relationship or a constraint that ties all these different numbers and variables together. So what we might do before getting into any of the maths is carefully have a look at the constraint there. What we can see first of all is that this x here, which is the height of our required triangle, and the hypotenuse of that triangle, in fact, add up to give 21. So I'll look back at the diagram here. If I put point P all the way here, and I start moving it again like that, you can imagine this corner being all the way at the top there. So the length of this hypotenuse of this triangle and the height of that triangle both add to give 21 centimeters. So that's something we'd like to keep in mind. So as we're going through that, you might have noticed while I was scrolling that you see a little table here with a bunch of values on it. In fact, what that table looks like is in fact just a data capture of every single height and area value from this diagram here. So as I moved this point P up and down, it created a data capture of all the different values that got generated. So what we might do before going to the analytical calculus section is in fact have a look at a graph that was created from all those data capture points. So if you have a look at this graph over here, you can see that the area increases as the value of x increases, reaches a maximum point like we saw before. It was around the x equals 7 and area equals about 42, and then it sort of comes down again. So this graph over here agrees entirely with the data capture that we've seen, as well as the diagram that we had over there. So just to quickly recap, the x, which is the height of the triangle, and the hypotenuse of the triangle both add to get 21. So let's start on with some analytics and some actual mathematics. So what we know is that from Pythagoras, the hypotenuse squared equals the height squared plus the base squared. So what we're going to do is we're going to generate one equation that connects these three quantities together. So let us start with the hypotenuse. And like we said before, the hypotenuse and the height of the triangle both add to get 21. Therefore, the hypotenuse and x, when they get to 21, we can let the hypotenuse be 21 minus x. So the whole width is 21. The hypotenuse is just going to be 21 minus x because the hypotenuse forms the remainder of the width. That is the hypotenuse squared done. And then we can equate that to the one side, which is x, and then square that, plus, go back to the diagram, and our base there, let's just call that base b for simplicity. When I hit enter, I just end up with the same equation there. What we want to do with that equation is solve for the base, because we want the area of this triangle, so we want the base and we want the height as well. So let us go to menu, then algebra, and then solve. So we've got the solve command ready to go. We're going to press up to copy the equation. Press enter, it copies it into the entry line, and a comma b, which solves for the base. Now, when we solve for the base, we see a couple of things going on over here. The main reason behind that is the fact that when you're solving an equation with a square in it, it creates a negative solution as well as a positive solution. The other part that's there, which is 22x minus 21 less than or equals 0, that's just a result of the domain of the function. So we know that the base of this particular triangle must be a positive. So let's ignore the negative version and end up with the positive one. So what we might do is in fact create a function called b of x, which is defined as that base over there. So I'm going to start by saying b, open bracket and x, and close the bracket. Now, a lot of you might be familiar with the define command. Well, there is another quicker way to get a define going, and the way to do that is you press Control, and then you press the template button. And if you notice carefully, on top of that template button, there's a little colon, semicolon, as well as an equal sign. That has the same meaning as define. So we're going to let bx be defined as that particular function at the top. So what I might do is just quickly go and copy that square root, hit enter, and it will be defined as that. So we now have a function for the base of this triangle in terms of the height x. So now that we've got the base, we now need the area of the triangle. So given that area starts with a, we always use a for the area. So I'm going to create a new function called a of x and use the exact same situation as before, Control template to get the assigned. And we know that the area of a triangle is 1/2, so 1/2 multiplied by the base, which is here. So the base, as we saw before, was b of x. Also notice how the value of b has gone in bold. That means that the calculator is basically giving you feedback that something is defined in b, and we just did that before. We've now got the base. Let's multiply that again by the height of the triangle, which happens to be x. Now hit enter and it just says done. So let's just quickly verify that the calculator has the correct function there, and we might just hit var and then press A for area, type x, hit enter, and then we've got that function there. So we can now do some calculus with that because that is a single function with a single variable. Just a quick recap. What our aim is to maximize the area of that particular triangle. So most of you might be familiar with the menu, calculus, and derivative command. I'm going to show you another way that I tend to use with my students, and that is the shift and minus. An easy way to remember that is shift and minus. It's minus because we are normally when you differentiate polynomials, you reduce the degree. So that's why shift and minus is a good one to do. So I'm going to put x there because that is the variable we're differentiating with respect to, and then go up paste that into the derivative, and hit enter. Now that looks quite clunky and messy right there, but what we can do, there's a really good command in here for making fractions look a lot simpler, and that's called common denominator. So how do we get there? It's menu, algebra, fraction tools, and common denominator. So it comes up with the common denom command. You press up, enter, enter, and now that looks much better. It's a much smaller expression. It's the same as before, but it just looks less clunky. So now we need to make that derivative equal to 0 to find the x value at which we get maximum. So pressing menu, algebra solve again, pressing up, equals 0, comma x, and we end up with the value of x equals 7, which pretty much agrees with what we saw in the interactivity before. So now that we know x equals 7, we can then go ahead and find the actual maximum area like the question stated before. The good news is we already have the area function. I'll just scroll back up to that. We have the area function sitting here. So we don't need to actually go and find the base and find the height and do Pythagoras and do all that again. We can literally just get the a function from var, press a, and then just type in 7, because that is the x value at which we get a maximum. Hit enter, and there we go, 49 square root 3 over 2. So that is the exact maximum area of our triangle. Let's just quickly verify that with our previous scatter plot. So I'm going to press Control Enter to approximate, and we get 42.4352, which is very close and pretty much agrees with what we had before. So let's just, I have one more thing to show you, and that is the actual area function agreeing with our scatter plot. So I'm going to go back to the scatter plot, which is sitting here, and let's try and graph the area function that we had before. So I'm going to go to Menu, Graph Entry, and Function. So as you can see there, f1x. So the calculator is basically ready and waiting for us to type in our function. The good news is that we have the area function defined already. We can press var for that, press A, and then press X. So that is the exact area function. We don't need to go back to our calculator screen and type in the function again. We've already got it saved in the calculator memory. We hit enter, and if you can sort of see in the background, we've got a graph there. What I might do is change the color of that to red. And what you can see is the red graph is the exact function that we had, that we generated the area from, and the blue dots are the scatter plot. As you can see, it's pretty much an exact fit, so we can be confident that our mathematics has worked well in this particular case. So before I finish off with that, I'd like to quickly show a quick extension of this problem. We might not have time to get through all of it, but I might just have a quick chat about how we can extend this if you want to do this with your students. So this problem basically regards a general piece of paper rather than an A4 piece of paper. So problem 1, we had an A4, everyone's used to A4 pieces of paper. Now we have a general piece of paper where we don't necessarily have a height of 21 centimeters. So the mathematics works out the same way, but the diagram looks slightly different. And the only difference we can see there is the W for the width of the piece of paper and L to be the length of the piece of paper. We can go through the same amount of mathematics and we'll end up with a particular sort of case that tells us in general what the relation of the width is to the x to be able to get the maximum area. So I might quickly go through that. We've seen the algebra already before, so this doesn't require too much explanation. So we can see that the width of this piece of paper is W, and the hypotenuse will obviously be W minus X. The W just replaces the 21 that was there before. So we have W minus X squared equals X squared plus B squared. Notice now how the B is not bolded, even though I had defined it before, and that is because we're now in a new problem. So you can see 2.3 up there before. before we were in problem 1. So when we are in different problems, the variables are not linked to other problems. They're separate like that. So I'm going to solve that for B, and we get a very similar sort of scenario happening. The only difference is we don't see 21, we see W. So yet again, I'm going to define the area of our triangle using the control template again as 1/2 times the base times the height, which is x. So again, we have our area there. Now let's go ahead and differentiate that. Shift minus. We get a derivative. Let's try making it a bit simpler with fractions. Common denominator. That looks a bit better. And then let's solve that for x. Algebra solve equals 0, comma x, and we get x equals w over 3. Now that right there is a brilliant result because this is telling us regardless of what size of paper we choose. So you can imagine that piece of paper to be as large as or as small as you want. So you can think of it as small as an A5 or as large as an A0 piece of paper. Regardless of the size of paper you choose and you perform this experiment, you will always end up with x equaling w over 3. So that is the x value at which the maximum area occurs. So that right there is our paper folding problem. I know that as math teachers, we struggle sometimes with thinking of scenarios. So hopefully with this piece of paper folding, sometimes we get a bit stuck, we get a bit crumpled, we get a bit crushed when we try to think of different problems. And hopefully this piece of paper problem gives you some ideas to use with your class or with the SAC or with an exam. Thanks, Brian.
Yep, certainly. And once again, all very neatly tying in. Thank you, Stephen. Comments from people watching saying that yes, that's great, and a lot. We've got a lot of people online tonight, but quite a few haven't even done that problem, which
I see.
I think it's a problem that's been about for a fair while, like that at least with an A4 piece of paper, and I know I first did it just with paper, getting students to actually fold it and measure the points and so forth, and therefore the areas get some values, and then we manually put it into the lists to then get a scatter plot. But of course, with the data capture, it just ties it all together so much more. So terrific, and thank you to both of our presenters this evening. And I think there's going to be some some pretty good SAC tasks coming out of this, I expect. So thank you to Stephen and to Ray. I'm just working to share my screen here with you. And if you get the opportunity to see these presenters at the one of the LEC events that we'll be running, we'll run a range of those across the year, and of course the big one that we've been running now on an annual basis at Mount Waverley in December, and then of course at the Maths Association Victoria Annual Conference, follow up on and quiz them more on these ideas. I'm about to close out the webinar, and when I do, can I ask you please to fill out the feedback and encourage our presenters along and thank them for the wonderful files that they're sharing with you. I thought it was a beautiful mix of some ideas where I know some of our participants will be looking to write and develop those files themselves. Others, I know, will be most appreciative of just receiving the files and then being able to go through those with their students. And then adapt them to, as I expect, a lot of those I think might end up becoming SAC activities, which is great. So you will be getting those in an email within the next couple of days, along with your PD certificate. Remember, if you saw it and you think a colleague who didn't see it would benefit from it, refer them to the YouTube channel, or also, of course, to the TI Australia website, where they can download the full view of this webinar. And any further questions, you can follow up with us. Reminder, I'm your host, Brian Lannon, and thank you also to our panellists, Raymond and Stephen. Good night to all.
Good night.
Good night.